Here I want to discuss geodesics on surfaces of revolution. In particular, we consider surfaces in 3 dimensions, and we start from the line element ds squared. Let me zoom out a little bit. ds squared can be written in the following form: dxi gij dxj, where I and j can be equal to 1 or to 2 because we need two parameters to describe a line element lying on a surface. So the geodesic equation can be written in the following form. We have the second derivative of xk with respect to the parameter ds squared. So s is the parameter along the geodesic, plus gamma kij, which is the Christoffel symbol, dxi ds dxj ds equal to 0. And the Christoffel symbols can be written in the following fashion: gamma kij equal to 1/2. Then we have the inverse metric tensor gkl dglj with respect to xi plus dgil dxj minus dgij dxl. Now, a surface of rotation can be written in the following form. So, for example, we have an origin O, and we describe a point P lying on the surface. So we want to describe the vector OP, which has 3 coordinates because we are in 3 dimensions, but we only have 2 parameters. For example, xy, and then we have f of the square root of x squared plus y squared. So this is how you can describe a surface of rotation where the z coordinate can be written in this fashion. And if we go to polar coordinates, this can also be written as r cosine theta, r sine theta, f of r, like this. So xi, our vector xi, consists of the 2 parameters r and theta. And basically we can calculate the elements of the metric tensor gij. For example, we can compute them like this: partial derivatives of the vector OP with respect to xi, and then we take the dot product with the partial derivative of OP with respect to xj. And another thing that one should keep in mind is that the mode of the differential of OP is equal to ds. Now, instead of doing all the calculations, I have prepared a MATLAB script here where I define basically the variables, and I calculate the metric tensor, the inverse metric tensor, and the Christoffel symbols. In particular, here on the top right, you can see the definition of G. So that's a calculation based upon the variables. So you can see that the non-zero elements are G11 and G22, and then here we have G inverse, and we also have the Christoffel symbols here, gamma ij1, which basically is the following object. It's a matrix, gamma ij, with these 2 parameters I and j, so these 2 integers, and then here the superscript is equal to 1. So this is a 2 by 2 matrix. And similarly, you can compute gamma 2 ij as a matrix, and it is still a 2 by 2 matrix. So we have their definitions, or actually their calculations, reported in here. So from these calculations, basically, we have all we need to write down the geodesic equations. So I will write the geodesic equations. They are 2 equations because we have integers that can take the values 1 and 2. So we have the second derivative of r with respect to s squared plus f prime of r, f double prime of r, divided by 1 plus f prime of r squared, dr over ds squared, and then we have minus r over 1 plus f prime of r squared d theta over ds squared equal to 0. And we have also another equation, d squared theta ds squared plus 2 over r dr over ds d theta over ds equal to 0. Now, the second equation here can also be written in the following fashion. We have 1 over r squared d over ds r squared d theta over ds equal to 0. Now, basically, this means that there must be a constant c such that c is equal to r squared d theta over ds, like this. And this means that if c is not equal to 0, we can rewrite this equation as ds equal to r squared over c d theta. And we can use this equation to substitute it in the definition of the line element. The line element is equal to ds squared, and this is equal to dxi gij dxj. But now we have defined the dxi, the vector dxi, which is made up of the two components dr and d theta, and gij has been calculated. In my case, I did it by means of MATLAB, but anyway, the calculations are really straightforward. And this element can be written like this: 1 plus f prime of r squared, and this multiplies dr squared, plus r squared d theta squared. Now we can use this equation that we have found, and we can substitute it here, and then we have a relation between the differentials dr squared and d theta squared. And this relation can be used to find the implicit form of geodesics. In particular, it's quite easy. You just simply have to separate the variables and then you integrate, and you can write down the following equation: theta minus some constant theta 0 equal to plus or minus c integral from r0 to r square root of 1 plus f prime of xi squared divided by xi square root of xi squared minus c squared dxi. Now, let's not focus too much on the actual form of the equation, but let me give you some comments. So, for example, if c is equal to 0, which we excluded at first, because if you remember, if you wanted to obtain this equation here, you have to divide by c. So we actually excluded c equal to 0. But if c is equal to 0, actually what you can say from this equation here is that d theta over ds must be 0. But this means also that this equation holds in that case, because if c is equal to 0, we have theta equal to theta 0, which is a constant. So if c is equal to 0, what we have is this condition. But what is this condition? This represents the fact that the so-called meridians are geodesics. And in general, if you consider meridians, you also have the so-called parallels, and they are described by the equation r equal to a constant. So if you want dr over ds equal to 0. But in general, we can see they are not really geodesics, because if dr over ds, or if you want dr is equal to 0, so r is a constant, we don't get geodesics. And let me show you from the equations that we have in here. So dr over ds equal to 0 basically means that this object here is 0, this one is 0, and you can see that this one here is 0 as well. So basically we have that d theta over ds must be a constant because its second derivative, I mean the second derivative of theta is equal to 0, so the derivative of theta must be equal to a constant. And from here, since this is a constant, we must impose the fact that f prime of r goes to infinity, right? So these are more special conditions that are fulfilled only in some special cases. For example, if we have a sphere, so we have z, x, y, and then we draw only the upper part of the sphere, so the semi-sphere. Now, I mean, this is just a simple sketch, but never mind. If we consider the line that's lying on the equator here, this is a parallel because r is equal to a constant here, where r is the distance from the axis of revolution. This is r. But if we change r and we take the derivative of f, which represents basically it's a curve that's lying in one of the planes coming out of the xy plane, or perpendicular if you want, because we have to rotate it in order to obtain the surface of revolution or surface of rotation. If we take the derivative of f, well, the derivative is the slope of the tangent line, right? So the only way to make this slope infinite is when we are here on the equator. That's, I mean, this is just a simple sketch, but you can understand why in general parallels are not geodesics, whereas meridians are geodesics.